Good morning, math people, mathematical folks, friends of the math. You know what it is? Spectral sequence time. Spectral sequence saga. Yeah, what else to say? Other than just, we're gonna dive back into it. So, where were we? I think we were here. I think we were coming up on definition 1.9. Locally finite graded vector space. So each piece is finite dimensional. Then the Poincare series is just the polynomial of the dimensions. On the face of it, it seems to carry very little information. But what is true? If A is globally finite dimensional, is globally finite dimensional. You and your homies are all specky. Well, you're about to get sequenced as well. And then we've got this tensor product structure as well. Okay, sure. And then the Euler characteristic, the oily boy. Our favorite oily boy is the alternating sum. Yeah. Okay. When it's graded algebra, aspects of the structure are reflected in the Poincare series. For example, the rational polynomials. Since this is a free commutative algebra and one generator, all of the powers of x persist in here and generated as a graded vector space, right? Wait, why? Huh? We're giving x degree 2 here? Surely this is a... Yeah, wait, what? Oh, sorry, we're giving it degree n? Oh, where x is of degree n, right. It's right in front of my face. And then more generally, okay, it'll be a product of that. Sure. Good morning, Mom. Whoa, you have the top fan badge in chat this morning. Congratulations. So, hello, Ownage Effects. You'd think I'd be able to read that name perfectly out loud now. So, whether the Poincare series turns out to be a rational function of T expresses a measure of the complexity of the algebra structure. Okay, sure. Some powerful numerical invariants derived from Poincare series have also been useful in the study of local rings. Cool. Wait, really? Oh, okay. So if you have bi-graded vector space, then we have the same polynomial, but we sum up the bi-gradings. Onage. I know I struggle every day to read it. I don't understand either. Yeah. Okay, so we have Poincare series, right, for the bigraded things. For example, if this is the example in 1E, right, that was the XYZ example, right, that was this one. Yeah. So one of each factor is coming from X, Y, and Z. Okay. Now, because HR is isomorphic to this sum, it is immediate that a filtered graded vector space has the same Poincare series as its associated bigraded vector space. So it is immediate. Oh man, I need to drink more coffee. It is immediate that a filtered graded vector space has the same Poincare series I see. I referred you to Aloufy. Aloufy chapter 0. This is Aloufy. Algebra chapter 0 by Aloufy. That's what I mean. It's a book everyone should have on their shelves. And I do mean everyone. Today you get interrupted writing Zig by a live stream. I don't know what that is. Some programming thing? You tell all bright undergrads you know to have Aloufy. You never read one page of it. Based. No, chapter 0 is the entire book. And he's never dropped chapter 1. And he has written books since. Yeah. Okay, we can compare Poincare series at each degree. We say that this is true. For example, whenever there's an epimorphism of locally finite graded vector spaces, and the bigger one's bigger. Zig is a programming language. I knew it. That you like to bully with math things. His earlier book has a cooler name, Algebra Notes from the Underground. That's his earlier book? I thought that was the new book, because didn't he put out a new book? He put out a new book recently that's like Introduction to Algebra, but with rings first. A textbook you might write could be characterized as a shorter Aloufy without algebra. I can also write a textbook very quickly, which is a shorter Aloufy without algebra. 0 pages long, though. I'm not super familiar with the Atiyah-Herzbach spectral sequence, unfortunately, but we're going to get there on this channel together. I also like math books with literary references, Boris. Like Hoop the Doodle, which is a Steinbeck reference, as someone told me recently. Good morning, Rod. You're starting to write a library for real tensors in Zig. Huh. Because the amount of tensor libraries and programming due to ML angered you. Yeah. Okay. Example 1e. We've got a spectral sequence converging to H, and E2 is locally finite. Then H is locally finite, and we decrease. Okay, so things start out big on the E2 page, and our Poincare polynomials diminish. Poincare polynomials diminish until we get to the graded vector space. And furthermore, the polynomials are equal if and only if it collapses. Finally, we let the Euler characteristic, sure, be evaluation at -1 whenever these expressions are meaningful. And then those Euler characteristics should be equal. Okay. Oh, see, someone was complaining about the accounting of indices. Now, you know things are about to get crazy because we're putting in the accounting of indices. Oh God. Do I want to read this proof? Look, there's examples. There's concrete examples coming up. So let's have a little look here. Oh, by real tensors, do you mean actual tensors? Why wouldn't you want a library of tensors over the reals? Okay. Let n be a fixed natural number, and let p plus q be n from elementary linear algebra. Right. Just our rank nullity theorem. Since the kernel is a subspace of this, we have for all pq these series of inequalities. Okay, this isn't so bad actually. And then by local finiteness, sum up over each of these. Yeah, okay. That's not so bad. We got the first part. We got the first part. Why wouldn't isn't a reason? You got me there. How about this? I like tensors. No, well, tensors, so Lockheed, you should go watch my truth about tensors video. I mean, a tensor product is actually something that can be defined over two modules. R modules for some ring. Right? You define a tensor product. This is well, maybe not the most general definition, because maybe the most general thing is to talk about a monoidal category. But or a monoid is maybe the most general thing, but that's too crazy. Well, it's not too crazy, but you can define tensor products of modules over arbitrary rings. And then where do you go from there? Well, then you define tensor product of vector spaces, because the real numbers is just a particular ring, so that's just a special case of that. And then finally, tensors that you use in physics or that you're thinking about is well, basically you need a vector bundle. You need two vector bundles, but then locally these things just look like vector spaces, and so you can, tensor up. A rod, you can tensor any two functors? What are you talking about? Tensors you worked with doing code were all Z tensors, which would be over a point, morally. I suppose so. Although, technically you should think of spec Z as a 3-manifold. You're trying to focus on tensors just in the context of Ricci calculus. Sure, yeah, in that case, you only need to worry about R. Okay, so if the spectral sequence collapses, of course these polynomials are eventually equal. Wait. Oh, yes. Yeah. Suppose, however, that these polynomials are equal. This is going to be the trickier part of the proof, I bet. Our first insertion applies this is true for all j. So to establish the collapse of the spectral sequence, maybe not any two categories, but between the same categories, where one is covariant and the other is contravariant. How do you define the tensor product of functors? Even in that case, I don't know how. Tensors on a manifold as being over the ring of functions. Was that true? I mean, when I think about a tensor, like a tensor in physics is very specifically, a section of the of TPQ of your manifold, by which I mean the vector bundle, which has p copies of the tensors and p copies of the tangent bundle, and q copies of the cotangent bundle, the dual bundle. And so, I mean, a section, this is like, it's a whole family of maps. Yeah. Now, if your space is sufficiently nice, your category of 3 manifolds should be, or sorry, what am I saying? I'm so mixed up this morning. If your space is sufficiently nice, then your category of vector bundles should be equivalent to the category of projective modules over this ring. Or is it oh, that's what you mean by gamma here. Right, I see. Sorry. Then you're right, Leo Lectures. Yeah, Spectral Sequence is live, but we're getting distracted right now. Is the covariant, contravariant stuff unavoidable? Most things end up being bifunctors. I guess while we're slightly on this topic, just to not spit nonsense, in your documentation, is there a canonical isomorphism between tangent space over manifold and Rn? Well, I mean, you have I think there is something about this. My master supervisor tried to explain this to me for something in my thesis. I mean, if you have your manifold, you have your and a choice of atlas, which you could view as like defining the structure on your manifold. Then these provide you I mean, maybe not canonical maps, right? Because you've got these overlaps. You've got these overlaps on U, but I guess it should be compatible in some sense if you look at the intersection. I mean, U gives you this map into Rn, and that is how you sort of define your local, how you get your local frames of your tangent bundle, is because then this induces a map like here, and then you define like dxi to be like the pullback of the local differential here, or something like this. Spec Z is a 3-manifold because if you look at its étal cohomology, it obeys some property that looks like the property that you would expect of a 3-manifold. Basically, if you look at like Poincare duality, and you have some pairing between your like homology and cohomology, and basically if you put the number 3 here and you look at the étal stuff, well, okay, it's not étal homology, but there's some other group there. But yeah, roughly that's the idea. It's not quite over the ring of functions, but a section of sheaf of modules, yeah. Yeah, maybe we'll go back to spectral sequences in a second here. Similar to being over R, if you're going over spec R. Yeah. A sheaf of rings. Yeah. The answer is no. If it's embedded in Rn, you can canonically, well, but embedding in Rn is very non-canonical though, so I don't know if I would consider that discounting. Yeah. You want to tune in and say that this is a crime. One should not discuss spectral sequences in public. Yeah, well, what can I say? I'm a bad boy. I'm bringing the dark basement to the internet. There is, what was I going to say? I remember drawing some sort of functorial diagram, though, when it comes to, there's some sort of natural commuting diagram, at least, you get when you're writing down the tangent spaces. It's somewhere in my master's thesis, but maybe it's not what I'm remembering it as. Yeah. Wait, you have to invoke axiom of choice at the start of your library's documentation? Why do you have to do that? Okay, where are we here? Back to the spectral sequence. So we have this. We want to establish the collapse of the spectral sequence. So we'd like to show that this is true. Now for all n, which is to say for all n, this is true. Since E2 it'd be the canonical representation for an embedded manifold, sure. So E2 is locally finite. It follows that since E2 is locally finite, it follows that ER is locally finite. Yeah. And the dimension of this is the sum of the dimension of those pieces. Wait a second. Why is he saying thus? I thought we were trying to prove these things. Hang on a second. Invoking axiom of choice to have some starting basis on the tangent space. relative to which store the components of the tensor. I don't think you need axiom of choice for that in general. I mean, yeah, you don't need axiom of choice for that. The finite dimensional vector space. And if you have, right, I mean, I mean, not only that, this whole process I said here about how you, like maybe it's not canonical, but you like if you have your charts, like if you've defined your manifold in the computer, which should amount to writing down some functions, some choices of coordinates basically, then from that you can like explicitly, write down like the local sections of your vector bundle, local frame. Choice is not needed at all. Yeah, exactly, as Arad said. Also, if you're computing on a choice function, I guarantee you that choice function did not need choice to construct it. Yes, exactly. Yeah. Okay, hang on. To establish, what did we say? To establish, we can show that this. Okay. So we're going to try to show that. For all n. Now, why is this true? Oh, because we're assuming. Because we said the polynomials are equal. Right. Okay, I see. We have this because we said the polynomials are equal. Right. Finite dimensional sequence at the airport? Can you get a quick rundown on what a vector bundle is? What's the best way? It is basically a family of vector spaces parameterized by some topological space. I don't want to get too sidetracked because there's a lot to say to define a vector bundle, but for example, you could imagine over the real line just sticking a one-dimensional vector space above each point in the line. So, this would, if you did that, you would get something that itself would just be isomorphic to R2, right, as the entire space. But you would sort of view this as being like a copy of R2 sitting above the real line. And it's a vector bundle. There's more to it than this, but it's a vector bundle because if you look at the pre-image of any point, you have a vector space, namely a copy of the real numbers. Similarly, if you were to draw a sphere and now the vector bundle, you don't draw any of these planes as intersecting, but you imagine the whole collection of tangent planes to the sphere as you move those around. And so to every point on the sphere, you're associating a two-dimensional vector space. Okay, there's a lot more technical things to define it properly, but the choice part only lives in the documentation, not the code. Yeah. Fiber bundle where fiber is a vector space. Pretty much. I mean, yeah, pretty much. There's something else about, a specific map is linear, but whatever. YouTube prevented you from suggesting doing Serre spectral sequence? Very strange. I mean, we'll get there eventually. A family of vectors, not a family of vectors, a family of vector spaces. So a vector space is a big collection of vectors, and now a vector bundle is a collection of vector spaces. Yeah, it's a freaky thing. Okay, Also, sorry, I know you sent me a couple emails. It might take me a while to respond, but I will. See ya, Leo Lectures. Go crush it at work. Or at work or working on math. Definitely crush it if you're working on math. If you're going to your job, save your energy for doing math, of course. Okay. Right, so where was I? I'm happy with the fact that each of these dimensions are equal. Since E2 is locally finite, ER is locally finite, sure. And this is true. Yes, I believe it. Thus, these sums are true. Yes, I believe it. And since the dimension is always non-negative, and these are bigger than this, then it can only hold if these are equal at every level. Yes, okay, great, fantastic. Okay, good to know there's no deadlines. Okay, so now, great, so we're done that part. That actually wasn't so bad. We got distracted, so it took us a while, but the actual proof was not so bad. Now we look at Euler. Now we look at oily boys. And we introduce the partial sums, blah. And notice that the limit is equal to this. Okay. So since those oily boys are equal, it suffices to show that that these are equal for all I. Right. So we use our favorite rank nullity theorem, and we compute. Okay, hold on to your hats. This is going to be quite the computation. Are those vector spaces necessarily tangent spaces in a vector bundle? The ones that we're talking about right now? No, absolutely not. Absolutely not. Or you mean for a vector bundle? No. 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 You can have much more general. A vector bundle in general is just sort of any like smoothly varying family of vector spaces above the base space. So it can definitely be much more general. And for example, you should expect that a lot of things you can do with vector spaces you can do with vector bundles, including performing operations on them such as direct sum and tensor product. And so if you have one vector bundle, you can then sum it and tensor it and to get a bunch of others. Okay. So we want to compute this partial sum. What is this? Okay, so we just split it open by rank nullity business. Just separating the sum again. Now what's happening in this next step? You know, if it was me, I don't like splitting things open like this. I would just have it on 3 separate lines. But maybe this was made when there was still page limits or something. Oh, we're pulling out L, right? What have we done? We've pulled out 0. We've pulled out n equals 0, and we've pulled out L. That's what we've done. Okay. Oh man. Okay. And this map should be what is going on here? Good morning, Brian. How goes looking at kernels and images? It's going. Dumb moment when you forget whether basis for tangent space used upper or lower index. Oh, yeah. That's not a thing I would ever remember. Oh, man. Okay. What's going on here? Okay, this is this part. This is this part here. This other term, sure. So everything here is supposed to be this? Yeah, I don't see that. This is hurting my brain. Why is that true? Why is that true? What happened to this? So is this term 0? And is it everything in these parentheses? No, because somehow we're adding that term back in over here. I guess we're using like a rank nullity. The construction is old-fashioned. What do you mean by that? What construction? Okay, I'm willing to just accept this part of the computation and move on with my life. This looks tedious. Are they trying to show that a sequence is exact? No, they're trying to show... we're trying to show that the Euler characteristic of a bi-graded vector space satisfies this property. Which is kind of about exact sequences. Anyway, so we get, this should just be the Euler characteristic of this. And then we've got this term sticking out at the end. So what do we do about that? Oh, and then we let L go to infinity. This incorporates the extra term into the limit. What? What? Incorporates the extra term into the limit? Huh? Now you got me confused. Euler characteristic does exist. Well, not a vector space, but a graded vector space. You're just taking an alternating... It's just an alternating sum of the... Yeah, it has a much more general definition, which agrees with the old one. This is very confusing to me, though. Why would this... Oh, I see. Right. This is just going to go to 0 because L is getting bigger and bigger and bigger. And that's the bottom starting point. Okay. Right. And eventually the differentials die. So I don't know why he's saying incorporates the extra term into the limit. That seems weird, but that seems like a weird way to phrase it. So maybe I'm misunderstanding, but I think that does it. There's a similar exercise in a Luffy, yeah, that a singly indexed chain complex has the same Euler characteristic as its homology. Oh, interesting. Well, I'm happy with where we are in the document. Okay, as an application of this example, if one wants to compute the Euler characteristic of a manifold, there you go. The job is simplified if there is a spectral sequence converging. So the E2 term of the spectral sequence, which may be known, can be used to determine the Euler characteristic even if our cohomologies are not known. Nice. Okay. Another piece of structure that can help in calculation with a spectral sequence is the presence of an action of a graded algebra on the target. Holy moly. Graded algebra on the target. That can be found on the spectral sequence. For example, the so-called Steenrod algebra, which acts on the FP coefficient cohomology in many spectral sequences. Looks like we've got examples coming up. Quite a ways down the line. We're still in chapter 1 here. A group acting on a vector space? Is that what that is? A group cohomology in a vector space that acts on the various equivariant topological invariants of a space on which the group acts. Interesting. Okay, so suppose we have a graded algebra. A graded vector space H is a gamma star module. If there's a mapping, okay, we've got associativity. Probably it's going to preserve the grading or grading increase in some way, right? Yeah, I mean, it should be the, maybe I'm wrong, but I'm guessing we're going to have something like, if alpha is in gamma R and M is in HP, then alpha M should be in like HP plus R or something. Probably we want that. As a reader might expect, we want to consider how graded algebra might act on the bi-graded vector space. In this instance, we only consider one such case of an action that represents the interesting case in later chapters. But more general definitions are possible. Okay. So it's going to act on a bi-graded vector space. It acts vertically. If fixing the first component is a gamma star module, and there is a module structure there. Oh, wait, so we're actually not increasing the degree. Oh, at least on the end component, which makes sense. You are back. So finally, the most important question. Do I think it's possible to master all of maths for a single student? No. It's not possible to master all of maths for anyone. It's not possible for a small group of mathematicians to master all of math at this point. Oh, not in a specialized way, but in a broader way? Well, I don't know what that means then. I don't know what that means. You could probably learn, you could probably learn most of the important basic definitions in every field. But, I mean, this sort of seems like a bit of an oxymoron, right? What do you mean? How do you master something in a broad way? I mean, mastery of a subject kind of implies a certain amount of depth. And so, yeah. And so, of course, any time you spend going deep on a subject is time that you're not going broad across subjects and vice versa. So, yeah. So I think in short, no, of course, there are people who seem to be able to make contributions to many different fields of mathematics. So it is possible to make non-trivial contributions to various different fields, but I wouldn't say that it's probable. And even then, you're going to face limitations, I suppose. What do I want to do with mathematics? I don't know. I'm just, well, I don't know if you're asking me or Goddard, but I'm just an addict. I'm just a math addict, and I just like drawing these squiggly symbols in my notebook. That's all there is to it. But yes, you're right. That question, that is the important question that should dictate the things you should learn and master. Yeah, I don't think you should. A polymath is way harder in this century to achieve. Yeah, in the sense of being able to have a reasonable understanding and of a field and converse, intelligibly with experts in a field. We just know so much more. So I think it's a silly thing to try and to have the goal, I want to master a lot of subjects. Why? I think you should want to learn about what you want to learn about. And then if that happens to bring you to a certain amount of breadth, okay. But it's very easy to spend a lot of time reading about a lot of different stuff and pick a different topic every day and convince yourself that you know a lot. But then, when the chips fall, you may find that actually you don't have any depth at all. It's good to find a balance, I think. I don't think that comment really makes sense. Category theory doesn't help you learn. Yeah, that doesn't really make sense to me. Category theory doesn't make it easier to learn all of these topics. Yeah, I mean, it's nice that we have a unified language, and it certainly can be helpful. If I tell you some pair of functors in one field or an adjoint pair, and you go, oh, okay, I get what that means. I get how that functions in that area. Sure. But, I mean, how does that help you learn differential equations, for example? Such a hypothetical person probably finished 3 generalizations of Langlands or something. Yeah. Category theory is a bird's eye view, not a telescope. Yes, that's a good way to put it. Category theory is not a foundation of math, even now. That's true. That goes to model theory or set theory. Those also aren't foundations for all of math. First off, math isn't beholden to any one foundation. There's people who are working in different foundations. So there's nothing that's a foundation for all of math. Unless you take the union of the different foundations and you say, okay, math is all of these axiomatic systems separately. Disjoint union. Then there's that. For you, the point of improving at math is not to know a lot, but to develop yourself in the tools and intuition to pick up whatever new ideas are thrown your way. Yeah. Then what is ETCS? I mean, that's a categorical... That's an effort to categorically, to try and capture the category of sets, purely categorically. But this still is not a foundation for all of mathematics. I am at... Should I even say this? Should I be giving out my public information? I mean, it's very easy. If you just Google my name, you'll quickly find out. So I guess I'll just tell you I'm at the University of Calgary. For now, I will be gone soon. I will be graduated soon, in less than a year. Anywho, now, well, not that I dislike getting distracted, but seeing as we're getting quite distracted now, and I have to go, I think that will be the end for today. Is statistics then a pure math or applied math? You do not see axioms in statistics. Well, there are axioms in statistics. There's the axioms of, well, depends. I mean, well, okay, this is complicated. I mean, there's axioms that underlie most of mathematics. But then you can still define the axioms of a group, but technically you could build all of that within the axioms of ZFC. So you can also take an axiomatic approach to statistics. But but then also all the math theorems and statistics can follow from ZFC. But ultimately, I mean, statistics, as opposed to maybe probability theory, you could maybe say is more pure math, and statistics is about the application. Anywho, I am going to go now.